There we go. Okay. So the first thing we want to do is, so really what we need is, we need the curvature to get the radius of this, right? So the radius will be 1 over the curvature. And then we need the normal vector in order to figure out where that center is. There's the normal vector is going to point right to the center of the osculating circle, right? Because it's always pointing in the direction of turning. So we really need that normal vector, whatever that is. N at, is this pi over 4? And then we need the radius, which is going to be 1 over the curvature at pi over 4. And once we have that, then we're kind of home free, because we can project this, we can magnify that vector by the amount of the radius. And that'll give us a new vector that will, if we put its tail at that point, its tip will be at the center. Something like that. So what is this? This vector is r times n of pi over 4. Because n of pi over 4 is a unit vector, so multiply it by r, and it will be the length of the radius now pointing in the right direction from this point, pi over 4 radical 2 over 2. And then if we just take that vector, and we're going to take its components are the change in x and change in y, right? So we just add those to starting x and y. It'll give us the final x and y, right? So really the only thing about this, so you can find this with a formula. So really the only thing is finding n. So how do you find n? So here's how I think about finding n. I can get the rate of change at that point. And I can do that by doing f prime of x is negative sine x. And so then if I take the rate of change at pi over 4, that's going to be negative radical 2 over 2. So my unit tangent vector then, is going to be in the direction of what? So like, think of rate of change is dy dx, so it's like the direction of this. If a 1 unit change in x would give you a negative radical 2 change in y, but then I need to get, well, it doesn't matter. All I need is the direction of n. I don't really have to find t, so I can actually use this vector. It wouldn't be t because it wouldn't be unit 1, but this, say, I'll just call it a. So this vector a, I could say, is 1 comma negative radical 2 over 2, and that would point in the same direction as t, right? If I unitize that, it would be the t vector, unit tangent. But I don't need to unitize it, because what I need now is I need the direction of n. So what would n be? Let's think about this. So if this vector has an x-coordinate of 1 and a y-coordinate of negative radical 2 over 2, let's see, I need to exaggerate that to see the picture better. So that has the y-coordinate's bigger, right? That's not that. So this has a 1 and negative radical 2 over 2, right? So if we know that this direction, is going to have a dot product that's 0 with this one, right? So do you see that if these are at a right angle, then the x component of this vector is like the y component of this one, and the y component of this one is like the x component of this one. Do you see that? In order to preserve a right angle there, so I could just, so what would this be? So this vector, say, call it vector b, would be, both are negative, right? Both are negative, and its y component would be like the x component of this one. So, sorry, its x component would be like the y component of this one. So negative radical 2 over 2, and then negative 1. So that's the direction of n. Did you see how I reasoned that out? So, and then just to check it, if you took the dot product of these two, it should be 0, right? So negative radical 2 and positive radical 2 makes 0. So that's my direction of n. I could make that a unit vector to actually get n, multiply it by my radius, and now I have this red vector. And that red vector, its components are the changes in x, so I could take pi over 4 plus the x component, and then radical 2 over 2 plus this y component, and that would give me the coordinates of the center. And then I got the center and the radius. Did you follow all that? Any questions? But this is a helpful technique in R2 to get an orthogonal vector. You switch the components. Do you see how switching the components gives you a vector orthogonal to your original vector? But then you got to make sure your signs are right. In this case, both signs are negative. If I'm pointing down and to the right with my original vector, then both signs will be negative for this orthogonal vector. So switch the components and get the signs right. Make sure your dot product is 0. That's a helpful technique to kind of really quickly get an orthogonal vector. It only works in R2. So in R3, that doesn't work. Yeah.
And the reason why I did this is I knew that I know it's a shortcut, but it only works in R2, and I wanted to factor the same normal vector in R3.
Okay.
And so is it only the tangent vector?
Yeah, it's just usually an awful calculation, right? So that's why you're just going to do it once for homework, and then you'll pay your dues, and that's it, all right? And then, but more importantly, is like, what is n? What does it mean? What direction does it point? That kind of. And so yes, to calculate it truly, it would be the normalized derivative or the unitized derivative of the unit tangent. And if you're in the written homework that you have for next week, that you have in recitation this week, it's kind of rigged, so it helps you a little bit. But if it's not if your original R function is not rigged, this is just plain awful, right? So this is just like you got square roots, and it's terrible. Okay. So, but I'll give you one that's somewhat rigged, so the algebra kind of is helpful. Do it once, and then you don't have to do it again. And then, but more importantly, do you know what all these symbols mean, and can you express things using the symbols? I'm much more interested in that. Okay. Other questions? Okay. That being said, can I erase this? Are we good? Last chance. Question? Okay. So I'm going to look at this one again, my favorite, right? So as I take attendance here, so this is R of t, okay? I want you to express this is a position function now, okay? So RT is position function. No, not backwards. No, it won't. Okay, so I want you to express then, given that the position function is R of t, express the speed function, express the velocity function, express the direction of motion function and the direction of turning function and the acceleration function. Just express those things. And then check for the speed function.
It would be the magnitude of R of t.
Magnitude of R of t? Like that?
Yeah.
Julian, you agree with that? That's what he wants for the speed function.
Yeah.
Gavin, you agree with that?
Yeah, I agree.
3. Rebecca says no. What is it?
It's the magnitude of R prime.
Magnitude of R prime. Magnitude of R prime. And is that a real valued / scalar function of t or a vector function? Yeah. So when we talk about functions, we're going to talk about real valued functions. That's what we mean by scalar function. So is that talking about the dependent or the independent variable when we say a real valued function? Is that the dependent or the independent? That's talking about the dependent variable, right? That what comes out of the speed function is, when you plug in a t, is just a number. It's how fast. Okay, what about the velocity function? Ryan, did you get that?
R prime of t.
And is that real valued or vector function?
Vector.
Right, so For every t, you get a vector. And that vector has what? Magnitude and direction. Okay, direction of motion function. What do you think that is? Sarah? RT over the magnitude of t. Nope. Quite. Yeah, Joseph? Richard, sorry.
It's R prime of t over the magnitude of
And what is that?
That's our t function.
T function, capital T. Unit tangent. Unit tangent function is direction of motion, right? Don't care about the magnitude of it, so we just make it 1 always. This gives us the direction of motion. So let me show you that one. Oh, so this is velocity. This is velocity, the blue one. Constant magnitude or changing magnitude? Changing, according to?
How much curve we get out of each t.
Okay, and if it's position, then the magnitude of this is? Magnitude of the blue one? The speed, right? Speed. So the length of the blue vector is your speed. And then the direction of this is? Capital T. That's the unit tangent, and that's this one. So now I'm showing you just the t function, right? Magnitude 1 always, pointing in the direction of motion. Okay, direction of turning function. Fernando, which one's that? What's that?
I think
Simon, yeah, Simon.
It's t prime of t over the magnitude of t.
And what is that?
That is n.
N. So the direction of turning is n, right? And that's always going to be at a right angle to the direction of motion. So if it's 0, what does that tell you? If that's the 0 vector, then what's happening? Not turning, going directly in a straight line. If you're going in a straight line, you'll get the 0 vector for n. But if that is a non-zero vector, that means you're turning in some way, and this is going to be the direction you're turning perpendicular to t, right? Okay, and then what's the acceleration function? Your best guess. We haven't talked about it yet, do they?
Is it like magnitude of t prime over the magnitude of r prime?
No. Yeah, go ahead.
R double prime.
Yeah, it's just r double prime. So it's going to be the derivative of velocity is acceleration. And I'll show you that. So here is r double prime. So let's go a little slower here. So I'm still showing the unit tangent, okay? So I'm still showing the t, but now I'm also showing r double prime in kind of orange there. So I want you to look at what's going on here. So look, it's pointing backwards, it's pointing to the side, it's pointing forwards, it's pointing to the side. What is going on with this r double prime function? So this is a complicated kind of weird thing, right? It's not, slow this down a bit. It's the gold one. The gold one, or the orangish one. And let's just go to so it's kind of crazy, right? It's like, what is going on with this vector? So any observations? What is going on with this gold vector that's pointing it seems to be pointing all over the place relative to the motion, right? Simon?
It's the direction it's turning in the way that it's like slowing down or speeding up.
So it's two different things.
Yes.
What were you going to say?
I was going to say, it's kind of pointing in the direction of the velocity or prime t is that what you turn it to. Like, it points that way, the velocity.
It's actually pointing in all different directions. It's pointing in the direction of against motion here, so it's opposite of motion. Now it's pointing kind of in the direction of n, right? And then here at the end, it kind of points in the direction of t. And then now n. And now t, or n again maybe. So it's complicated what's going on here. And so let's talk about, we want to kind of make more sense of this than just r double prime is the acceleration, because acceleration is a complicated thing. So we want to, and so Simon was on the right idea there that actually acceleration is kind of broken up into two different aspects. And when we split those apart, then we can easily make sense of both of them separately, and then just trust that when we add them together, we get this r double prime, which kind of combines them both. All right, so let's talk through that here. Okay, so don't try to go word for word here. Make sure you good note taking, you're listening and getting what's important. All right, so if r is the position function, then we said r double prime is acceleration. Okay, so acceleration is due to two phenomena. There's two things going on here which combine to give you r double prime. And the first is what you normally think of as acceleration is speeding up and slowing down. Speeding up and slowing down, right? If you're driving in your car, you think of accelerating, you think of like excitement, right? You know, like you're being pushed back in your seat, okay? And your tummy feels weird, okay? All right, and then there's turning, all right? So, but turning also contributes to acceleration. So what direction is speeding up, slowing down? What direction would that be? So we think of our representations of different things. So speeding up, slowing down would be what direction?
Would it be parallel to the velocity?
Okay, and so what direction is that? When you say parallel to the velocity, we have a vector for that. What direction is that?
Forward or backward?
Forward or backward? It's t, right? So that's our capital T. So speeding up, slowing down, that part of it is in the direction of t. And then we have part of the acceleration, there's acceleration due to turning. And what direction is that in? N, right? So that'd be n. So we can dissect acceleration into the amount of speeding up, slowing down, and then that would be times the t vector plus the amount of the magnitude of turning times the n vector. And that would give us this r double prime vector. So it's the sum of the tangential acceleration vector. So this is the tangential acceleration vector plus the normal acceleration vector, or turning acceleration vector. Add those two together, you get this r double prime. So that's why what I showed you is that just the plain old r double prime is going haywire, because you have different contributions of speeding up and turning at different times, right? And so then sometimes it's like all turning and you're not even speeding up or slowing down. So it's going to point in the direction of n. Sometimes you're going straight and you're speeding up, so it's going to be mostly in the direction of t. So that's why it was going all over the place. Okay? All right, so here's the derivation of it. So we can determine these a sub t and a sub n, these real valued functions, right? So these are real valued functions separately. We can do that by taking the derivative of r prime. Okay, so r double prime is the derivative of r prime with respect to t. So we can write r prime as the magnitude of r prime, which is v, so this is just simply the magnitude of r prime, times the t vector. Would you buy that? So we can rewrite the velocity as speed times direction, right? Times the unit in the unit vector in the direction of motion. So how do we take the derivative of that? We've got, this is a function of t, the speed is a function of t, and the unit tangent is a function of t.
First and second, second first.
Right, product rule, right? We're going to have to do product rule. So when we do product rule, it looks like this. Derivative of the speed times t plus the speed times the derivative of t. Okay, so now to get this into a form that's going to be more useful, to kind of work back towards this form here, we have to recall some previous formulas. So this kind of, it's a parentheses here, in parentheses. Recall this definition of curvature and n. Okay, so curvature was the rate of change of direction per amount of arc length swept out. So that was this. That was our kind of our meaning of curvature formula. And then this was our, of course, that was our unit normal formula. So we're going to use this to solve for t prime of t. We're going to use these two formulas to solve for t prime. All right, so t prime is basically equals this times this, right? You solve for t prime. And then we're going to substitute in magnitude of t prime as curvature times this. So when you put these two together, solving for t prime, you get this. And this is just so we can rewrite our r double prime result of the product rule here. So t prime is, so this right here is this times this. But then our magnitude of t prime is this times this. And so you put it all together and you get curvature times the magnitude of r prime times n is t prime. So we're going to substitute that in for that. So when we do that, when we make that substitution, this is what we get. And so now that looks like what we said originally. So this now looks like this. And we've found out what the acceleration in the tangential direction and the acceleration in the normal direction is. What's the acceleration in the tangential direction? Yeah, so that's just the derivative of the speed. Derivative of the speed is rate of change of speed. So that's your acceleration. That's just speeding up or slowing down, right? It's just how your rate of change of speed. Makes sense, right? And then what is our acceleration due to turning? Well, that turns out to be the speed squared times the curvature. So the faster you're going around a curve, the more you're accelerating in terms of curvature. And then the higher the curvature, the tighter the curve, the more you're accelerating in the direction of n. So our tangential component of acceleration is just the derivative of the speed, and the normal component of acceleration is the speed squared times the curvature. So alternatively, in order to calculate these, there's alternative formulas for calculating a sub t and a sub n. Now, are these real valued functions, vector functions, one of each? What kind of functions are these? Vector functions or real valued functions? These are real valued functions. These are just give you numbers for any time t. These give you values. Now, we're going to take that value and we're going to multiply it by the unit tangent. And we're going to take that value and we're going to multiply it by the unit normal. And that will give us the acceleration vector. All right, so the tangential acceleration, there's another formula for that. Would it be a matter of the dot product of r prime and r double prime, or the cross product, if we want acceleration in the direction of motion, right? Would that be dot product or cross product? Dot product, right? Because we want those, how much those are in the same direction, right? In the direction of motion. So that's dot product. So the normal would be, if you take r prime and r double prime, you want how much they are orthogonal, so that's cross product. So these are alternative ways to calculate the tangential acceleration and the normal acceleration based on the r function, right? So this is based on r function. It saves you from having to calculate the curvature function, which could be messy. All right, so these are real valued functions, but say AT times t, that's the vector valued function for acceleration in the direction of motion. And then a sub n t times n of, that would be the vectored valued version of that. So these components of acceleration, you can talk about them as scalar functions, or you can have them as vector functions just by multiplying by t or n, whatever applies. So those are the real valued versions, and then these are the vectored valued versions. By adding together the vector valued versions, adding them together gives you r double prime. That vector function, by adding them together. Okay, did all that I said make sense?
So is v of t, that's the speed?
Speed.
That's not the velocity?
Velocity would be r prime of t. So v of t is the magnitude of r prime. Yeah, anywhere on here where I have v of t, that's the magnitude of r prime. R prime is velocity, v of t is the scalar magnitude of that. So it's the speed. Okay, questions on those? So I'm not going to take the time in class to work through the formulas. Just if you just got to know your vector multiplication, your dot product, your cross product, okay, and you can do it. Okay, so it's just following the formula correctly. But then I'm most interested in you knowing what all the symbols mean relative to motion and space. Okay. Any questions? Okay, let's change gears then. Here we go. We'll talk about what's called multivariable functions. Oh, so let's one more thing. And now let's make heads or tails of what we're seeing here now that we've talked about it. So why is the acceleration kind of pointing backwards here and it's kind of large? Why would that be? In this part of the curve at the beginning, it's kind of pointing backwards, and it's kind of has a large magnitude. Yeah.
It's slowing down and sort of turning towards us.
Okay, so it's a little bit of turning, but not a lot. But it's slowing down. So because it's slowing down, the acceleration will be in the opposite direction of motion, right? Okay. Now on the loop, what's happening on the loop? What do you see? So what does that tell us about tangential acceleration around the loop? Yeah, David? Okay, but what about the tangential acceleration, like speeding up or slowing down? What does that show us there on the loop?
It's pretty small.
Yeah, there's like, it's not, right? It's like maintaining a constant speed around the loop, so you don't have a component of acceleration pointing forward. It's like the whole thing is pointing in the direction of, what direction? N, right? So like all the acceleration now is due to turning, and none is due to forward motion, like speeding up or slowing down. So it's pretty much in the direction of n. Okay? And then now what about now? What can you say about the motion right now? Or can you about?
It's not turning very much.
Not turning, right? It's like straight line. And are we speeding up or slowing down? A lot or a little? Here's the unit tangent, here's the red one, and then here's the r double prime vector. So it's just speeding up a little bit and not turning, right? Speeding up a little bit and not turning. What about now? Well, is the speed changing much? Speed's not changing much, right? So because all the acceleration is due to turning kind of downward, right? Turning downward. And then what about here? Oh, I turned it off. So there's one point here where it's like, how about that? Slowing down a little bit and not turning, right? Slowing down a little bit and not turning. We get the gist of it? So this r double prime is the combination of those those two, and so it's much easier to talk about them separately, right, and analyze things separately. Okay, very good. Last chance, questions on acceleration. Okay, multivariable functions. So most functions you've encountered so far in your life, in your math career, have been this kind, y equals f of x. So what do we call this? This is called a single variable, real valued function. This is a single variable, real valued function. So when we say single variable, we're talking about, is that independent or dependent? Single variable. It's talking about one independent variable. Single variable, I mean one independent variable. Real valued is concerning that the dependent variable is a number, a changing number, right? It's a changing value. And so single variable, real valued functions are what you've spent most of your career working in, right? So what would this be? So now we've done these, right? Space curves. Space curves. So how would you describe this function? What kind of function is this? Single variable or multivariable? Single variable. Real valued? Vector valued, right? So this is a single, so our space curves that we've been working, we just got done with, were single variable vector valued functions. Right? So we have a single parameter that tells us what vector we have, right? So then what is a multivariable real valued function? Who could describe what a multivariable real valued function would be? What would that be? Yeah, Paul.
Like z equals x squared plus y squared.
Okay. So two independent variables give you a z. Exactly, right. So multivariable would mean you have more than one independent variable, and then based on what the values of those variables are, it spits out a single value, right? So it's like this. Z is a function of x and y. So multivariable, and based on what those two values are, you get a real value. Okay, so here's a good example. So a wave height function. Wave heights in the ocean are a function of two different things. The speed of the wind, and then how long the duration of that wind has been blowing. Okay, so I was in Rocky Point last October, and usually the waves are, moderate, but there was one afternoon where the waves were so big that your teacher was kind of getting scared playing in these waves, okay? He was scared he's going to hit his head because they were huge. And why were they huge? Because all day long, the wind was blowing very hard, okay? So the speed of the wind was high, and it was for several hours, and that created these very high wave heights. So this is the idea of a real-world multivariable function. So if you have a low wind speed and t is very high, well, you're still going to have probably not very high wave height, okay? Or if you have a sudden huge gust of wind, high speed, but it only lasts a second, well, it's not going to create these huge waves instantly, right? Okay, so that's an example. Okay, so we have lots of different representations. We have to be fluent in all the different representations of these multivariable functions. So the first one is, Paul picked my example, z equals x squared plus y squared. And so now z equals x squared plus y squared has this alternative way of representing it as f of xy. F of xy equals x squared plus y squared. We already know what is this multivariable function? What is this thing? F of xy equals x squared plus y squared. Remember? That was our reference paraboloid, right? It was the one that has the vertex at the origin and opens up, right? So this is the first type of representation. It's like a formula or a function definition as a representation of a multivariable function. And so your formula now will have two variables in it. or it can have 2, right? So f of xy equals square root of y. Is that a multivariable function? Yes, yes. What about this? Is that a multivariable function? Yes. Just like f of x equals 3 is a function. F of x equals 3 is a function. Even though there's no x's in your formula, for any x, it's just that your dependent value is 3, no matter what x is. Okay? So these are all multivariable functions. It doesn't have to have an x and a y in the formula. Okay? But x and y are varying, and as they vary, you get different values of the dependent variable, in normally z. Okay, a graph in R3. So what's the graph of f? What's the graph of f? We just talked about it, right? Now, so how do graphs of, so this is a two-variable real-valued function, graphs in R3 as a, this was a paraboloid, but in general, surfaces, right? We're going to guess surface because what we have is an equation of x, y, and z. We talked about that before. When you have an equation of x, y, and z, that graph says a surface, right? So these multivariable functions, when your dependent variable is z, f of x, y is z, you're going to get a surface. In this case, we get the standard paraboloid. So this is specifically if you have a two variable function, right? A two variable function. You get a surface in R3. Okay, so we talked about traces, and so when we do traces with these multivariable functions, we like these the best. The traces where z equals k, and we call those level curves. Level curves are curves of the surface that are all at the same level, so the same constant value of z. Okay, and then put all those level curves together, and you get what's called a contour map, or it's like a topological map. You know what a topological map is? Shows elevation, right? So it's like looking down. So that's a full representation of a multivariable function. So what would the contour map look like for our paraboloid? Well, we're going to look down on the xy plane. And so it's the set of level curves for constant values of z. So what would that look like for the paraboloid? Parabolas? No, so the contour map is going to be now in the xy plane, and it's going to be a set of curves that are level curves for constant z's. For instance, z equals 1, z equals 2, z equals 3. So these will be circles, right? So when z is 1, 2, 3, 4, 5, you're going to get different circles. And each of those circles represents a constant z. So tell me about those circles. If I was to do it at integers, what would be true about those circles? What's that? They'd spread out as you go away? Okay, you got the right idea. So we're looking down on this. So constant z values. We're going to get concentric circles, circles of the origin, right? But what will happen for higher and higher z values? Further apart or closer together or the same distance apart? So remember, so it's like this, right? Paraboloids like this. Further apart as we go up in z? Closer together. They're going to get closer together. Because what the rate of change is increasing, right? The rate of change is increasing. So you go up the same amount as z, and you have a steeper and steeper edge, right? That your edge is getting steeper and steeper. So those circles are going to get closer together. I'm sure this is going to be horrible, but I'll do my best. Not bad. Furthest apart towards the origin and close together as you come up. Right, so the steeper the surface is, the steeper, you don't have to move much to change z a lot, right? We'll talk more about that. So you get the idea. Okay, a table of values. So table of values would give values of z for different not just x's, but ordered pairs, x and y. So let's create the table of values for f above. So now that table would be a two-dimensional table, right? And this would only be the first quadrant, right? This will only be the first quadrant where x and y are positive. So 0, 0 is 0, 1, 4, 9, 16. Then we'd have 1, 2, 5, 10, 17. And then add 4 to all those, right? This is 4. Did I do it right? Did I have the right numbers? That was for 2. Do I got the right numbers? Do you see what I'm doing? It's just given an x and a y, what's z? It's x squared plus y squared. So you could, this table of values then is a representation of that function f. So all of these are representations. Formula, the surface graph in R3, the contour map, or the level curves in R2, a table of values. These are all valid representations of a multivariable function. So let me just show you one. Okay, so this is a contour map. These are level curves, and it's the numbers telling you what z value. So this last line down here is a z value of 3. This line right here is a z value of 2. Z value of 1 is on the x-axis. Z value of 0.4 is up here, etc. So can you imagine or sketch the surface? Can you imagine or sketch what surface this contour plot is representing? So again, you have to kind of, this is the x-axis, which is here, right? This is our y-axis, which is here.
Exponential cylinder.
Okay, Alex, tell us.
Just a guess.
So as you go in the negative y direction, what happens? Z values do what? Z values get smaller? No, in the negative y direction, they get bigger, and they're getting closer together, right? So what does that mean? Going down faster? Going up faster. So as we go in the negative y direction, our z value is increasing, and it's increasing faster and faster. Do you see that? And then as you go in the positive y direction, we're going down in z, and at a lower rate. What about if you move in the x direction? No change in z, right? No change in z, your constant z's. So that's why, so we do have a cylinder, right? Yeah, and indeed this is an x, so this is 1, like this. So it looks like this. Do you see it? So Alex nailed it. Exponential cylinder. can just turn it on. I love it that you all just want to stay around. It's great. It's time to go.